All right. All right, why don't we go ahead and get started? Okay, hi everyone. We are thrilled to roll out the latest episode of the Quantum Seminar Series, which is dedicated to the research and academic quantum communities. This Qiskit seminar takes place every Friday at noon Eastern Time and is hosted on the Qiskit YouTube channel, so you can subscribe right here to make sure that you don't miss any future episodes. I'm your host for today. My name is Olivia Lanes from IBM Quantum. The usual host, Zlatko, is unable to join us today, but nevertheless, I am very excited to be here and to be speaking with Professor Archana Kamal, who I am pleased to introduce right now. Professor Archana Kamal did her bachelor's degree at St. Stephen's College at the University of Delhi in India and her master's at the Indian Institute of Technology before she moved to Yale to continue studying quantum physics and quantum information for her Ph.D. She then moved on to MIT for her postdoctoral work before joining UMass Lowell, where she currently works as an assistant professor and a PI for the Quest Group. She has received numerous awards, including the Sterling Prize Fellowship from Yale University and the 35 Innovators Under 35 from the MIT Technology Review. So please join me in welcoming Archana today, who will be talking to us about generating and characterizing quantum correlations in NISQ systems. Archana, how's it going?
It's going well, Alea. Thanks for inviting me for the seminar. I'm thrilled to be here.
My pleasure. Happy to have you.
So
we can just bring up your slides whenever you are ready.
Yeah.
And I should mention that if anyone has any questions, I'm going to be monitoring the chat throughout. So feel free to just type your questions in the chat and I will get to them as soon as we can. I'm still seeing the presenter mode, so we just have to switch to the other setting.
Does this work?
Perfect. Yeah. Okay. So yes, if you have any questions, just type it in the chat and I will get to them as soon as we can. And yeah, floor is all yours.
Okay. Today I'll be talking about the recent work our group has been doing on generating and characterizing quantum correlations in noisy intermediate scale quantum systems. Right now, as many quantum enthusiasts and researchers know, we are what John Freskel termed as the NISQ era, where we are having quantum processors which are not fault tolerant or fully error corrected, but we have some respectable number of qubits ranging from 50 to 100. And they are noisy systems, of course, because as I said, they are not fully error corrected or fault tolerant. But there's a lot we can do with these systems, or at least we hope to do with these systems. And that is essentially the primary goal, in at least for the next 5-10 years in front of us, while we build towards a fully fault-tolerant quantum computer. What are the useful applications we can use for such systems? And in these next systems, we have both analog and digital versions which are coming up. Some of them are using hybrid algorithms. Some are completely analog systems which are quantum annealing. You also have digital versions like VQE solvers. And these are some of the applications which these systems are being actually used for. Some of these have been actually done by IBM itself. As you can see, the quantum chemistry simulation of a few atom molecules to actually understand the ground states of complex systems. Similarly, quantum many-body simulations. This is coming back to the original dream of Feynman that, quantum simulates quantum because it's very inefficient to simulate these kind of systems on classical computers. And similarly, as I said already, there are also quantum annealing and optimization things, which are actually very poorly understood systems, I would say, theoretically. Still, there are lots of open questions. There are no, standalone results like Shor's algorithm or prime factorization, which exist for these systems. But they are very generic in their appeal because a lot of optimization problems like transfer sizing models can be solved on these systems. So in all these NISQ era systems, it's the noise which ultimately limits the scale of computation we can do and how efficiently we can find these solutions like ground states of complex problems. So what is the problem of noise? The noise is essentially the Achilles heel of quantum computers. And primarily, this comes from uncontrolled degrees of freedom, which we also call environment. And these uncontrolled degrees of freedom essentially act as some kind of bath, which we call in physics language, which essentially sucks energy and information out of quantum computers. And there have been a lot of mitigation strategies which people have developed over the past decade or so. One of them is robust qubit design. This is there are two approaches to it. One is intrinsically coming up with very noise resilient qubits, like 0 pi qubits, or actually also a lot of materials engineering, developing materials which have very nice interfaces so that there are no defects, which are essentially the primary problem, for instance, superconducting qubits. There's also the very, very big field of quantum error correction, and there have been some very recent nice work in having logical encoding in very exotic states. Similarly, there's a lot of promise in topological quantum computing, where the entire model of quantum computation is based on some kind of a global symmetry or braiding operation. And particularly the last two, both quantum error correction and topological state, basically rely on non-local encoding of information, and what we call entanglement, the magic word. And the idea is that since you encode your information non-locally, then the local noise sources will not affect or be able to wash out the information which you have encoded in your qubit or quantum processing. So this sounds very promising, and this is essentially this is a milestone on the path towards fully fault-tolerant quantum computation. However, entanglement itself is very difficult to generate and characterize in the presence of noise. So in some sense, the question arises, have we traded off one problem for another? We essentially do non-local encoding so that we can protect quantum information, but this non-local encoding is in itself hard to generate and characterize, especially when you try to do that in the presence of noise. So this is what my talk is about. So it's broadly characterized into two parts, generation and characterization of correlations. And Olivia has promised me that she is going to keep an eye out for your questions. So please do feel free to interrupt or put your questions in the chat. So let us go to the first part, which is the generation and characterization, the generation of the quantum correlations in NISQ systems. So as I said, quantum systems, the real quantum systems and qubits we work with, they are not, unfortunately, the textbook harmonic oscillators and hydrogen atoms. They essentially are always talking to some uncontrolled degrees, which we call the bath. And let me see if I can use my laser pointer. Can you see my laser pointer? So here,
yeah, I see the pointer.
Great. So here, the evolution of some quantum state, which we define with this density operator rho, has some Hamiltonian evolution, which you do want, but some unwanted evolution, which you do not want. And the entire focus has been, at least the dominant focus in the past decade, has been on Hamiltonian engineering, where you want these kind of Hamiltonian, which is driving the wanted evolution in your quantum system fast enough such that you can ignore the non-unitary part. So that's what we want. And you can also correct for it actively by using some kind of a gate-based quantum error correction, dynamical decoupling. So these are all the things where we are trying to make as perfect a Hamiltonian or as fast as a Hamiltonian we need. But then in recent era, there has been kind of these other ideas which are very interesting, which are called reservoir engineering systems, where you say, okay, instead of beating decoherence, let's make it our friend, and control decoherence can help. So essentially, you deliberately couple a quantum system to an auxiliary system, let's say AMSILA, which overwhelms the coupling of the quantum system to the uncontrolled degrees of freedom. And this auxiliary system itself can also talk to the bath. But typically, the idea is to have this kind of hierarchy of coupling schemes, that the most strongest coupling is between the quantum system and the intended dissipation. And the idea is that if you design this correctly, then your quantum system can actually condense into this logical state you want. So this is actually the idea of dissipative quantum computing, that it's interaction with the environment which steers the quantum system towards this logical answer, if you want. So here the decoherence is your friend. It's of course has to be controlled. And this is what the focus is. The first talk is that especially in the NISQ era systems where you cannot really read decoherence, how do we actually control it properly? So again, let's just put some symbols on it for shorthand. So let's say the quantum system, which is in blue, is interacting extremely strongly with some kind of a controlled dissipation channel or ancilla system, which you have deliberately introduced. And both quantum system and the dissipation channel or the ancilla themselves have some weak couplings to uncontrolled degrees of freedom. And if this G is much stronger than the gamma, then the effective dissipation rate, which you induce on the quantum system, can overwhelm any kind of uncontrolled dissipation rate. This is the regime which we want to be in, that the dissipation which we are engineering, that overwhelms any other local dissipation channel. And the nice thing about this approach to correcting quantum systems or compensating for errors is that typically these systems have what are called continuous wave interactions, which means you're not using gates, so you're not actively controlling or doing some very complicated pulse engineering on the system. Another thing is that these kind of gamma rates, which you are actually inducing on the system deliberately, are tunable in situ, which means you can typically control the intended dissipation rate by just controlling the form or the strength of this G. And another very important part about this approach to correcting errors is that it's immune to state initialization. So there are no spam errors. So irrespective of where the quantum system, whether it starts out in a mixed state, or basically mixed state is something which doesn't have any coherence, whether it starts out in the ground state or some not preferable state, it will still be steered towards the correct state towards the end of its evolution. So that's why these target states are actually called what are called gas states. It's a funny acronym, but it actually stands for globally asymptotically stable states. Globally, because any initial state has kind of an attractor solution towards these target states. And asymptotic because in the limit t going to infinity, which of course we never wait for infinite times, but on times which are long enough, the system is guaranteed to settle into the target state you desire. And these kind of ideas have actually been already implemented in lots of platforms like superconducting circuits, trapped ions, Rydberg atoms, because of the inherent robustness to the noise this approach gives you. So before we go further, I would like to actually tell you briefly about because this whole idea of dissipative quantum computing kind of turns the decoherence on its head. So let us see what is essentially the control space or the parameter space. And the best way to think about this is to actually consider the eigenspectrum of what is this combined object, which is describing the non-unitary evolution. It's called the Liouvillean. Just like we calculate the eigenstate of the Hamiltonian, you can calculate the eigenstate of the Liouvillean. So as I said earlier, you have this unitary evolution part and non-unitary evolution, and the combined evolution is governed by what is called, we just combine the two and call it a Liouvillean. And this is what the spectrum of the Liouvillean can look like. Since non-unitary evolution is allowed, it doesn't only have real eigenvalues, it can have complex eigenvalues. So here you can have also, this is a typical spectrum of a Liouvillean. You always have a steady state of the system, which corresponds to the eigenvalue 0. And then there are other states, which are actually not very physical density states, density operators for the system. And they are separated from your steady state by what's called a spectral gap. So this gap is essentially the asymptotic rate at which system settles into its steady state. Now the steady state can be pure, which is what we are usually interested in, or mixed. A pure state is essentially which you can describe by a wave function, whereas an impure state you cannot even describe by a wave function, you have to write down a density matrix. So a gas state or a globally asymptotic stable state is realized when your steady state is an eigenstate of the Hamiltonian and a null state of the Liouvillean or the dissipative, which essentially means that by definition, the dissipation doesn't do anything to its steady state because it's actually kind of a ground state of the noise. So once the system is in its steady state, the noise is not acting anymore on the system. Similarly, you can also have a situation where you do have the steady state as the null state of your dissipation, but not an eigenstate of your Hamiltonian. In this case, even when you are in the, even when the dissipation has stopped acting on the system, the Hamiltonian kicks the system out of that steady state, and then dissipation keeps acting on it. And this actually leads to a mixed state. So you actually do get a steady state, which is unique, but it's no longer pure. And then there are some even more interesting ideas here where you can have multiple steady states. So for example, you can have a situation which is similar to the unique mixed state, but instead of just having one steady state, this bullseye orange thing just tells you that you have multiple steady states now, where which are actually null states of your dissipation, but not really eigenstates of your Hamiltonian. And because of that, you can actually end up with multiple steady states which are mixed. And in this case, the which steady state you get essentially depends on your initial state. And this is actually the regime which we have recently studied in a Kerr oscillator. It's very well known that there is actually a bistability which you see in nonlinear oscillators, and depending on where you initialize the system, you end up in a different steady state. And then the really intriguing part of this phase space, if you want, is when you can have multiple pure steady states. This is essentially the idea of what is called the decoherence-free subspace, or DFS. It was initially proposed by Lidar and co-workers, where the idea is that you can actually have multiple, you can have a kind of a subspace of your complex system, where at all times, not just in the steady state, the dissipate, it's decoupled from the dissipation. So the collapse operator or your dissipation or your Lindblad operator, never for all times is like it's a zero state. It's a null state. And within this DFS manifold, you can actually have coherences or different, like a Hamiltonian evolution. So it looks like a unitary evolution within an open system, which is very interesting. And this is essentially the idea of autonomous quantum error correction. This kind of behavior is also seen in critical phenomena in phase transitions. But today in this talk, I won't have time to cover this. So I'll be mostly focusing on at least how to realize a unique and pure steady state. So this idea is actually not very new. This was originally proposed by Peter Zoller's group in 2008, where the idea was, okay, you, as I already said, the necessary and sufficient condition is to actually have to engineer a steady state, which is the eigenstate of your Hamiltonian and the null state of your dissipator. And there are multiple, and one of the simplest schemes is, let's just try to create a Bell state or the EPR state. So you have two qubits. They are talking to some kind of oscillator. It can be some other reservoir. The harmonic oscillator is the simplest reservoir. And it's a reservoir because it itself couples weakly to another Bath mode. And this because of this coupling, it actually has some kind of a dissipation. So therefore, if the qubits have to decay, in the presence of the strong coupling, when this G is very strong, the preferred channel of decay is through the oscillator. It doesn't decay directly outside. It shuttles the excitation of the oscillator, and then the oscillator decays the excitation. And you have some local drives on the qubit. And typically, the way to analyze this system is that this is, let's say that the qubit system, this is a 4-level system, which I am trying to draw in this way, in this some kind of these are, GG, GE, EG, EE, some kind of a states. It can be, in fact, be even a singlet state or a triplet state. And then depending on how many excitations are in your resonator, you can just take this manifold of 4 states and just repeat it in the Hilbert space of the resonator. Now, because of the coupling of the system and Bath, you can actually, this kind of coupling essentially leads to a joint excitation of the qubit and the oscillator. So you can basically excite to some common state of the joint, some joint state of the qubits and the oscillator. And using the cup of the oscillator, it decays to this preferred state. As you can see, so for example, here, there are some local Rabi drives on the qubit. So you essentially create some kind of a coherent superposition of GG, triplet, and EE. This is excited to the bath. Then the triplet couples to the singlet, and the singlet is preferentially decays to this singlet with zero excitations of the bath. These schemes have been implemented even experimentally. But as you can see, these resonant driving schemes, they necessarily have to talk to the target state through some Hamiltonian coupling. This, which essentially means that you have to drive the qubits at resonance so that you can actually create some kind of a manifold through which you can pump out excitations through the bath and come back to the target state. So this is basically a coherently coupled manifold, which is then excited with some higher excitation number in the bath and then decays back. What happens is, because of this presence of this coupling, the Bell state in these or the target state, in this case, this is a Bell state. The Bell state is only a perturbative state of the open system dynamics, which means if you try to make this protocol faster, you also pump more and more population from the targets that you are trying to create. Now, what that leads to, that there is kind of a trade-off between how much error you can have in the steady state and how much time it takes to prepare the steady state. So if you try to go very fast, you also compromise the fidelity of the state you are preparing. Because the whole point is you have to always be at resonance. So you have to drive slower than the dressing of your state because of the coupling which it is having with the rest of the states. So because of this, there is this kind of a, if you want, a gain bandwidth trade-off for reservoir engineering, where there is, this is the error in your steady state. This is the time it takes to prepare the steady state, and the product is actually a constant. And because of this, if you want a very high quality target state, you have to wait longer, which is not what we typically want. So in our recent work, what we have tried to do is to actually break this trade-off. And one way to do it is to actually do the reservoir engineering in a bath selective way. And our preferred way to do this is actually to use the circuit QED platform. So for people who do not know circuit QED, basically the idea is to actually engineer a strong static interaction, which is shown with these dashed lines between your qubits and resonators. And depending on the state of your qubit, it actually shifts the frequencies of your resonance. This has actually been a standalone platform for most of the progress in superconducting qubits for quite some time. So if I now try to do the same diagram which I was doing earlier, here now, depending on how many excitations are there in my resonator, the qubit states are different because they have shifted by what are called dispersive shifts. These are the dispersive shifts which are induced because of these black dashed lines. These are the static couplings. And now, in addition, I can have some time-dependent couplings, which I call parametric couplings, which can excite my qubit and bath jointly, just like on the previous slide. But now the point is, if I choose the frequency at which these couplings are activated, I can ensure that unlike the previous slide, which was where you see here, the blue arrows look the same in all manifolds, because it's just these arrows do not understand or do not know about the state of the bath. But in the number selective, what I call the number selective driving schemes, depending on how you choose the frequencies, some interactions can be resonant, whereas some interactions can be off resonant. So for example, this difference frequency is off resonant in the one excitation manifold, where there's some frequency is off resonant in the zero excitation manifold. Now, because of this, you can immediately see that now my target state actually has no coupling, no coherent coupling, no blue arrow is coming out of the target state and coupling to the rest of the states. The only way this thing can be populated is from above, by if this state decays using kappa to this state. Now, because of this, the target state is now not a perturbative, but an exact state of your dynamics. Now, so this is an example of what this number selective driving, how this is implemented. You see here, I initialize my 2 qubits in the ground state, and depending on the state of the bath, whether it is 0 or 1 or 2, now the swap between GG and EE only happens in the single excitation manifold. It doesn't happen in either when there are 0 excitation in the resonator or 2 excitation in the resonator. So this is the meaning of actually having path selective interactions in the system. Similarly, we can do hopping between the states. So for example, here there's a hopping between GE and EG, which are the orange and the green states, but this is activated only in the 0 excitation manifold, and there is no hopping in the 1 and 2. You see that there are certain, this is the top panel is actually the RWA Hamiltonian or the effective Hamiltonian. But even if you do the full simulation, which is the lowest panel, the lowest row, you see that there is some leakage, but this leakage can be actually corrected by using some additional drives or by playing some other tricks, which I'll be happy to cover if you guys have questions on that. But the idea is that you are trying to activate some interactions in the system, but those interactions are selected based on the state of the bar. Once you're able to do that, what happens is that using this condition driving, it completely, as I said, it eliminates completely any coherent coupling or exit channel from the target state. So now you can simultaneously optimize fidelity and speed of your protocol. So this is what this is showing here. This is a kind of a parametric plot of the error in your steady state and the time it takes to prepare the steady state. The dashed line is what we get for the resonant driving schemes. As I said earlier, here the error and time are anti-correlated. So if you want low error, you have to take longer. Whereas when you do these number selective state stabilization schemes, you can keep increasing your coupling and your error and time both decrease simultaneously. So you can actually get very high fidelity states in very short times. So instead of epsilon times tau being constant, it's actually epsilon divided by tau, which is now constant. So it's a completely different qualitative regime of dissipative state stabilization. So I would like to actually, let's see what exactly happens in these kind of schemes and why we are able to achieve this in these kind of state stabilization schemes when we can have the parametric couplings. So for doing that, sorry, I think there is some, I'm having some problems with my PowerPoint.
I see a gray screen now. Did it disappear?
Yeah, I think the problem is I'm, running any application on my laptop is like, asking an old man to climb a Mount Everest. So let's see. I fear it might have hanged. Let's see if I can. Can you, sorry.
No worries.
Let
Maybe
me
just reshare.
Let me just restart the PowerPoint. I think it crashed. Sorry about that.
No worries. While you're bringing it up, we had one question.
Yes.
Maybe I'll just ask it while we're waiting. Somebody was asking, I'm not sure even what slide this was related to because I was trying to pay attention, but somebody asked, if we have these different types of entangled states, how does that relate to how much dissipation occurs, if that makes sense?
Yes, so let me actually, let's see if I can. I'm trying to reshare my PowerPoint, sorry.
No worries.
Does this?
I see it now.
I have to probably swap the setup.
Yeah, just swap the view and it'll be back to normal.
Okay. Sorry about that interruption.
All good.
So, yeah, so coming back to the question, yes, so it is true that entangled states actually So entangled states in some sense protect the information from non-local by actually encoding it non-locally. But in some sense, they're actually more fragile to decoherence because not only they are sensitive to local decoherence, but also correlated noise. So, which is of course the case, if you are making something correlated strongly, then, LS will also be affected what Bob does. It's basically that. But the exact nature of how robust they are to this correlated noise does depend on the kind of entangled state you have. So the answer is that for local noise, all entangled states are the same in some sense. But when it comes to correlated noise, different entangled states have different sensitivity. So for example, G at Z state is in some sense most entangled, but in some sense also the most fragile state. Whereas states like W states or cluster states are relatively more robust. Does that answer the, I hope that answers the
Yeah, it makes sense to me. I think that answered it.
Okay. So as I said, let's see why this is what exactly is the optimality regime and why these kind of schemes are able to minimize both the epsilon, the error, and the time required to get that error simultaneously. So here I'm actually showing the error and the time as a function of the ratio of kappa over G. So if you, this ratio of kappa over G can be kind of thought of as the ratio of the total dissipative coupling versus the total coherent coupling. Kappa is the dissipative rate and G is the total coupling rate. And you see when kappa over G is very large, then your error in fact does decrease with kappa, but the time keeps increasing. So error and time are anti-correlated. And when you go to the opposite regime, when your G dominates, then your error increases with kappa, whereas your tau starts decreasing. So you see, in some sense, we are, if you try to always push very hard on anything, it's kind of, to some extent, counterintuitive. You would think that you would want your G very strong, but that actually never pays off because in either very, very strong dissipative coupling or in very, very strong coherent coupling, let me try to save it. Yeah. In very, very strong dissipative coupling or in very, very strong coherent coupling, you always have anti-correlation of these goodness metrics. It's only when they are comparable that you have this kind of a Goldilocks zone of reservoir engineering. So you never want, you actually want to establish a balance between the errors which are generated because of your coupling and the errors which are generated because of your dissipation. So in some sense, you never want too little or too much dissipation. And your performance is always optimized when G is comparable to kappa. So of the order unity. This is kind of the, if you have to remember one message from this part of the talk, that is it. That, when you are doing reservoir engineering, it's kind of a weakest link problem. It never pays to push too hard on any one of these things.
So before you switch to the next slide, someone in the chat is asking, what if kappa equals G exactly? Or we see something special at that point? I mean, I'm sort of looking at this ratio on this graph here. It's at that boundary line.
Yeah, so actually, when I say kappa comparable to G, I just mean it's, order up to a factor, p-factor, which is order unity. So if it is few, like it doesn't matter whether you have a 0.5 versus 2, but it does matter if you have a 0.05 versus 20.
Sure.
Yeah, so it's order unity. So exactly whether it should be 1 or 2 really depends on the exact parameters of your problem.
Okay.
It's comparable. And one other nice thing about having these kind of tunable interactions is, typically you have stabilized a state and it's perfect, but what to do with it? You don't want to just stare at it and and you probably want to do something useful, some quantum computation with it. So the nice thing is that depending on the phase which you have on these drives, which are actually giving the dissipation on the system, if you change the phase, you can also tune in situ between different states. So for example, here I'm showing a 2-qubit Bloch sphere. It's not, you must have seen a single qubit Bloch sphere. This is actually a 2-qubit Bloch sphere. So the North Pole and the South Pole are actually product states, and the equator is actually a manifold of entangled states. And here, this is actually an even parity. It's a Bloch sphere of even parity states. And depending on the phase of your drives, you can either be in GG plus EE or GG minus EE. So you can actually do some kind of a NOT gate if you want, or a coherent control while remaining stabilized. And depending on the frequencies of the couplings which you are choosing, you can select the parity. Depending on the phases, you can choose which state you are in, as I'm showing here. So in fact, having this kind of tunable dissipation allows you arbitrary state preparation and control without leaving your stabilization manifold, which is very nice because this also allows us or gives us hope that we can do the entire logical quantum computation while remaining in these noise robust states. And in fact, there are some experiments which are currently going on these schemes, realizing these schemes at NISQ Boulder and Raytheon VBN, which I won't be covering in this talk. So this is where I would like to summarize the first part of the talk. So here, as I said, the primary message is that if you're doing any kind of reservoir engineering to protect your quantum states from errors, there should be always a balance between your coherent and dissipative rates. It does help to actually have some kind of number selective or state selective reservoir engineering, because as I showed in this one particular example, you can have trade-off free entanglement stabilization. You can have dissipation mediated coherent control of your stabilized state. And in fact, there's something which we have not covered in this talk at all, but for people who in the audience who care about these things like directional amplification, we recently showed how these kind of reservoir engineering principles show that you can actually change the bandwidth over your system is directional by just setting the bandwidth of your dissipation or the ancilla mode. And right now we are in the process of generalizing these systems to have a multi-partite entanglement stabilization. So, this was just an example of Bell states, but ultimately we want scalable solutions to generate no entanglement. And we want to extend these to higher dimensions where we can actually have dissipation-assisted topological protection. And there are some really interesting connections to quantum cosmology and quantum thermodynamics. So are there any questions on the first part? Because after that, we are going to go and see how we can actually characterize these kind of correlations.
I think we're all caught up. I think I have asked the questions that arose so far, so I'm good. I'm on the same page.
Great. Okay. So the second part of the talk is more about, will be, now we are shifting gears and we're saying, okay, generation of entanglement is already tough, but what about characterizing entanglement? And the short answer is that it is tougher, especially when it comes to NISQ systems. So what is the problem? The problem is that we want to characterize multipartite correlations in noisy quantum systems. So, and we want to do that in an efficient way. So let's say that you have a d-dimensional quantum system and it has some n-body correlations. And so you have some d to the power n states. But what you want to do is you want to measure only a low weight observable, which means it's m local. So for example, if you have, a 10-qubit system and 6 of them are entangled, you don't want to measure something which is a 6-qubit observable. You still want to detect it using, maybe low weight means 2, or maybe 2 is probably already hard enough, 2 or 3 weight, 3-qubit observables. So that's what, in fact, this should be much, much less than n. So that is the problem statement. The motivation is that we want to characterize the exotic phases of matter. So for example, this is this naturally occurring mineral called Herbert Smithite. So you get one guess to see who discovered this crystal. It's actually a Kagome ferromagnet. It's a quantum spin liquid in its ground state. So it's these kind of things are very, very attractive to condensed matter theorists. These kind of actually understanding how these correlations develop in quantum systems is also required to constrain low energy effective descriptions of not just ground states in complex condensed matter systems like this crystal, but also in cosmological observables, because we all know that early universe was small, and when things are small, they're quantum. So to actually understand quantum dynamics in cosmology, this is also quite important. We obviously want to do error correction in the presence of correlated noise. So almost all the quantum error correction codes, they assume spatially and temporally uncorrelated noise. So we actually do not have any codes yet, which really develop, which really correct for correlated noise, except barring maybe a couple of examples. And of course, from the point of view of the last part of the talk, we also want to have maybe non-trivial baths where maybe a bath itself is entangled, and then it talks to a system, and we do not quite yet know the full power of those kind of dissipation engineering protocols. And if you look at the current state of art, it's actually a little humbling because we only know how to characterize entanglement. We have a necessary and sufficient criteria to characterizing entanglement only in these 2x2 and 2x3 systems. Above that, we actually do not have any reliable metrics of detecting entanglement like correlations. In fact, witnessing noisy entanglement. So not even so for pure states, we still have some metrics, but for noisy entanglement, witnessing noisy entanglement is actually a computationally hard problem. In fact, if you want to have if you have a given density operator and you want to find if it has entanglement or not, with an accuracy which is 1 over some poly n, where n is the size of your system, then it can be as hard as an NP hard problem like PSAT. So the hope is that it's not quantum hard. Maybe it's not QMA hard for people out there. So that is the reason that people still think that maybe we will never be able to characterize all classes of entanglement in such systems, but for specific classes of entanglement, we should be able to at least certify these kind of states, if not detect them in any general way. So as you can see, there's a lot to be done in this field. So we have done some very baby steps, which I wanted to share with you. So in fact, surprisingly, when we were thinking about this problem, we actually got inspiration from classical systems. So in classical non-Hermitian systems, and especially photonics, there's this whole concept of exceptional points in these systems, which are essentially, if you want, some kind of degeneracies in these open systems. So in this degeneracies essentially appear as singularities in these open system parameter spaces. So just like we have degeneracies in Hamiltonian systems, we have degeneracies in noisy systems. These are special kinds of degeneracies. That's why it has this kind of self-aggrandizing name called exceptional point, because here not only the eigenvalues become the same, even the eigenvectors become the same. Whereas in Hamiltonian systems, the eigenvectors remain orthogonal, and just the eigenvalues become the same. So that's why this is the main difference from the Hamiltonian systems. And in fact, these exceptional points are realized at these are really point singularities in the parameter space. So they are very highly sensitive to noise. So in fact, this high sensitivity to noise makes them exceptional sensors. Every bad qubit is an excellent sensor. That's the idea of exceptional points. So from the point of what has it had got to do with the strong correlations or understanding detecting entanglement, interestingly, these exceptional points also mark the onset of strong correlations in open systems. What this means is that when an open system goes from weak coupling to strong coupling, which means weak coupling means that your Hamiltonian coupling is much less than your dissipative coupling, whereas strong coupling is when your Hamiltonian coupling is much larger than dissipative coupling. The transition point is set by this exceptional point. And in fact, in the spectrum of your system, it manifests itself as what is called a normal mode splitting. So you typically see a single, this is like a spectrum of a qubit or a cavity. And when it goes past the exceptional point in a strong coupling, you see the split spectrum, which we know as what's sometimes called the vacuum Rabi splitting, or just Rabi splitting if it is happening without vacuum noise. It happens even in classical systems, actually. Okay, so this is the point of how these exceptional points of singularities connect to the presence of strong correlations, because they are the point at which the system starts entering the strong coupling or the strongly correlated regime. Okay, so we are going to try to understand how this So this exceptional point physics or these strong coupling physics can essentially give us some clues to where, what kind of correlations can develop in open systems. So as I said, these exceptional points, when they are plotted in the parameter space, the parameters of my problem are basically these some G's, that's the coherent couplings, and some kappas. And let us, for the purposes of concreteness, consider a one-dimensional chain of open systems, which are coupled to each other through some coherent couplings, and each system has some decay. And here I am plotting the exceptional points of the system. So these lines are the exceptional points. And as I said, these exceptional points tell you the threshold of weak versus strong coupling. So anytime your system is sitting inside these curves, you know it is weakly coupled. Anytime it is outside, where there is this white region, you are strongly coupled. So the intercepts of these axes are basically what are called EP2s. So whenever you have an EPN, N means the dimensionality of the system. So EP2 is the strong coupling or the exceptional point for a two-mode system, and EP3 is an exceptional point for a three-mode system. So for example, for n equal to 3, you have a single EP3 in this parameter space. So it's pretty efficient because, as you can see, this diagonalization actually happens in the operator space. This is not in the state space, because let's say these are oscillators. So let's say if you have two oscillators and they have 10 states each, if you diagonalize in the state space, you have to take into account a 10 to the power 2 state space, which means you have to diagonalize in 100 by 100 some state space or Hilbert space. But when you actually diagonalize it in the state space, it's just a 2 by 2 matrix. So we are actually able to do this kind of crossover into the strong coupling regime in the operator space. So it's pretty efficient actually to study the emergence. You do not know what kind of correlation has emerged. You just know it is correlated. So it's more like a binary classification problem. You know whether you are correlated or not. So you don't, as I said, you don't have any information about the nature of correlations, and you also don't know what is correlated. Okay? So this is the problem which we wanted to solve. And what we did was, I fear that my laptop is again hanging out, sorry. Let's see if I have to start again. I'm sorry about this.
It's all right, no worries.
Are there any questions in the meantime while my laptop is deciding whether I have to start this presentation?
Well, we did have one question, and I'm not sure if I'm able to, I'm not sure I understand it completely, but they asked basically, what is noisy entanglement?
Noisy entanglement is when you have entanglement between density operators. It's not, so typically, you write something like when you have an entangled state, you write the full state can be written as a superposition over basis states. But for noisy entangled states, it has to be written as a superposition of density operators, not wave functions.
I see. Okay.
Okay, let's try this again. I really apologize. It's usually not this
No problem.
whimsical, but now I guess. Let me start this again.
Okay, great.
Anyone else? Okay. Okay. Thanks for your patience. Okay. So, as I said, we don't have any information about the nature of correlations in the strong coupling regime. We just know it is strongly correlated. So it's more like a yes/no answer. So the question is, can we know something about the nature of correlations? Because that's the whole problem which we are starting with. So here, as I said, we developed a new method which we thought, okay, people always think about eigenvalues. What about the eigenvectors? When you are diagonalizing a matrix, you always get eigenvalues and eigenvectors. So can we solve this question by just using eigenvectors? So in some sense, as I said, eigenvectors are special in open systems because at these degeneracies, they become parallel instead of orthogonal in the closed systems. But let us just not worry about the phases of these eigenvectors. Let's just take the lengths. And if you basically take away the phase information, then this whole idea of parallel versus orthogonal goes out of the window. We are just going to use eigenvectors like we use for Hamiltonian systems because we have actually thrown away the phase information. So 0 degree versus 90 degree doesn't matter anymore. So let's just see if we can do strong coupling by saying, okay, I know that when my systems become strongly coupled, my modes should become indistinguishable, right? I should not be able to say whether what is A and what is B because I should be in some coherent superposition of A and B. So can I just use my eigenvectors and say that if I'm strongly coupled, I will always have equal participation of all the modes. And in fact, we know that this does work for two-mode systems, then two-mode open systems, because we know that both A and B modes participate equally when we are looking at these systems. And this is what it looks like. But when you have, let me see if I can get laser pointer. Yeah, this is what it looks like. But when you have the N mode systems, they actually do not. This actually does not work because even when they are completely correlated, all the modes are not equally participating. And furthermore, depending on what decay rates these different modes have, you actually can have these numbers can change. So this will not work. You cannot just say that equal participation means strong correlation. Okay, what about we don't have equal participation, but as long as two modes look identical from the point of view of each eigenvector. So for example, in this regime, where I have put this question mark, this red question mark, you can see that these are my eigenvectors, psi1, psi2, psi3. And if you just inspect them, you would think that mode 1 and 3 always look the same in all the eigenvectors. So they must be strongly correlated because the system doesn't distinguish between 1 and 3. And in fact, that answer would be wrong. In fact, 1 and 3 are not strongly correlated in this regime. It's actually 1 and 2 and 2 and 3. So you should ask, how do I know that? And that's what I'm going to explain in the next slide. So what we actually found was, in fact, it doesn't work if you actually look at eigenvectors, the individual components of eigenvectors. We should actually look at planar projections of these vectors. And this is actually intimately tied to the idea that when you're thinking about correlations, you should think about some joint property. So you should not look at axial projections, but some planar projections of these eigenvectors in planes which are spanned by modes J and K. So imagine that you have n modes. You create n choose 2 pairs, and then look at projections of these eigenvectors along different planes which are formed by these pairs. And depending on the length of the eigenvectors in these different planes, if there is an eigenvector for which the projections in these JK planes is greater than all other eigenvector projections, then you say, okay, then modes J and K are strongly coupled. So in some sense, planes where the eigenvectors cast their longest shadows, they are strongly correlated modes. So this is actually an example or a figure for that. Let's say that you have a 4-mode system, and these are the eigenvectors, which are three are drawn in red, and 1 is drawn in black. And these 3 eigenvectors actually cast long shadows in A1, A2, A2, A3, and A1, A3 plane. But they actually cast a very small shadow in, let's say, the A3, A4, or A2, A4, or A1, A4 plane. If that is the case, then you will say, okay, my modes 1, 2, 3 are strongly correlated. So in fact, when the dominant planes form a kind of a closed subspace, you have formed a, 1, 2, 3 are forming a closed subspace, which are agreeing that, okay, in each of these planes, which are forming a 3-dimensional subspace, the eigenvectors shadows are the longest. Then in fact, that is sufficient and necessary to detect that you have a true three-way correlation in the system. So in fact, this kind of geometric method of understanding eigenvectors can actually tell you what is the correlation map of your system. So this is what it looks like for eigenvalues. And based on eigenvectors, this is the full map which you get. So in fact, here we have plotted different regions, and each color represents the satisfaction of that inequality which I showed on the previous slide. For example, in region 2, the modes 2, 3 have the longest shadow. Similarly, in region 1, the plane spanned by 1, 2 has the longest shadow. And in region 3, both 1, 2 and 2, 3 are strongly correlated. And interestingly, as you can see, that does not mean that 1, 3 is strongly correlated. In fact, there is only one point where all three are strongly correlated, and that only happens at this point C. And we recently, in the interest of time, I would just say that we recently applied this to actually a cooling system, where typically you couple a target system to an oscillator to cool it to its quantum ground state. And for a two-mode system, you can easily find when this quantum ground state cooling will saturate. As soon as the system enters a strong coupling regime, which is shown in this dashed line, the population begins to saturate. But when you have a complex bath which is correlated, you actually cannot know based on eigenvalues when the hybridization starts and when the cooling starts to saturate. But based on this eigenvector map, we can find out where the cooling is supposed to saturate. And I'll be happy to talk about this more. But let me actually focus on the correlation part. So similarly, this is actually a slightly more interesting system. This is n equal to 4 open chain, which you can immediately see it as a much more complicated phase diagram. We have actually 4 regions and 6 types of correlations. In fact, eigenvectors alone are sufficient to capture all the spectral features which are given by eigenvalues. As I already said, this also shows that the strong correlations are not associative, even though they are commutative. So if 1 is strongly correlated to 2 and 2 is strongly correlated to 3, does not mean that 1 is strongly correlated to 3. You can see this from this map that, in 3, 1 and 2 are strongly correlated and 2 and 3 are strongly correlated, but only at point R is there a true three-way correlation. Similarly, we also can detect using this idea, the super exchange type phenomenon. This is a thing which is seen in quantum chemistry in complex molecules, that if you have true strongly correlated subspaces, and there's a very, very weak coupling between them, you actually get a bigger correlated subspace. So in fact, you can see this as you go from point S to point, which is this point S, to this some region 4, where you have strong correlations between 1 and 2 and 3 and 4. But as soon as you turn in a small G2 coupling, which is correlating which is connecting these strongly correlated subspaces. So as soon as you move away from the axis, you actually get a square, because a very strong, very weak coupling between very strongly correlations can lead to multiple strong correlations. So in fact, I just wanted to emphasize this, that by using eigenvectors, we can actually do a full characterization of the coupling depth and the connectivity of the physical subsystems. This is the most important part, that we can actually find out where to look for correlations. You know where the strongest correlations exist, so you can go back with your toolbox of entanglement criterion and only focus on the subsystem and find out which class of entanglement you have. So just to summarize this part, connection. So we can actually connect what is the generator of the evolution which basically means what are your parameters like coherent couplings and dissipative rates, and the form of correlations which they lead to. And this is extremely important for this co-design approach of NISQ-like systems, where you want to engineer Hamiltonians or dissipation with the correct strength and correct form to achieve a given kind of state. Similarly, we can actually have k-fold correlations or k-fold degeneracies, which are detectable with just pairwise projections. And this we have done for quadratic Hamiltonians, so which is probably not quite surprising, because these are quadratic Hamiltonians. But it's still quite interesting that even such quadratic Hamiltonians can show many mode correlations, not just two mode correlations. As I said earlier, this kind of diagonalization works in operator space, so it's pretty efficient because you don't have to worry about the exponentiation which happens in the state space, which with the size and the dimensionality of the system. And most importantly, this eigenvector method allows you to do a physical subsystem identification, which essentially means that you know where the strongest correlations exist, and you can go and do your tomography there. And in future, we want to generalize it to truly quantum systems. True quantumness means nonlinear systems, which are not even classically simulatable. And here we are working on combining ideas from dimensional reduction, which are used in machine learning for feature recognition and tensor networks. Similarly, we want to see the scalable solution. Is this method scalable? Because as I said, here you are not diagonalizing in the state space, you are only diagonalizing in the operator space, which is a huge reduction because the operator space only scales linearly or polynomially within. But the question is, you have to identify the correct operator. So is this an equivalently hard problem than trying to study entanglement in the state space? We don't know that yet. There might be some, quantum censorship hypothesis which prevents us from doing that. So it may not be scalable. We have to see. And then, but maybe we can still not detect all kind of correlations, as I said, but we can earlier. But maybe we can just certify a fixed class of correlations. So, for example, you may not be able to identify all kinds of correlations, but you might be able to say, okay, is it GHZ type? Yes or no, by using these kind of methods. And finally, we want to actually extend this and connect this to the ideas from holographic entanglement, where you are not detecting what is the nature of entanglement. You are only studying if the entanglement is how the entanglement scales with the system size. Is it scaling as the area, or which is called the holographic entanglement, or the volume of the system? And that itself can be some very interesting measure of this entanglement. So finally, I would like to acknowledge all the important people who do all the work, especially Emery Doucet, who is a graduate student who did some outstanding work on dissipative state stabilization. A hat tip to all our theory and experimental collaborators. And with that, I will open the floor to questions. Thank you.
Thanks very much. We had a lot of people who said this was a really interesting and great talk. One question I saw a little while ago, which interests me because I'm an experimentalist, was this is going back to the first half of the talk, how does one actually go about engineering some of these baths that you talk about, like in a physical system? Could we maybe talk about that?
Sure. So actually, I was trying to not show long Hamiltonian equations. But let me, let me go back to the slide. Yeah, so for example, let's say you want to engineer this kind of interaction, right?
Yeah.
So basically, you would have you want to have a swap between GG and in this case EE, right? Red and blue are GG and EE. So
Okay.
typically, it means that you have you need to have an XX interaction between the qubits, because you want some kind of a sigma 1 dagger, sigma 2 dagger, correct? Mm-hmm. But in addition, you want it to be conditioned on the state of the bath, right? So basically, that means what you would do is to actually pump this, so let me actually go on this slide. This might be actually easier to see. We are essentially saying, okay, I want to have omega 1 plus omega 2, where omega 1 is the frequency of the first qubit and omega 2 is the frequency of the second qubit. So let's say I pump an interaction at the sum frequency. So this is a kind of a parametric interaction which will create an excitation in qubit 1 and qubit 2. But now you can choose your omega 1 and omega 2 at this frequency. This omega 1 is different from this omega 1, and this omega 2 is different from this omega 2. because as the bath has one photon, both the qubit frequencies have actually shifted a little. So now let's say I should actually not pump at omega 1 plus omega 2. I should pump at omega 1 plus omega 2 minus chi 1 minus chi 2. Because of that minus chi 1 and minus chi 2 part, it will actually be off resonant here, but it will be resonant here. So in some sense, you can select the interaction frequency, and that's why the parametric interactions are important. You can select the frequency of the interaction at which these things are resonant, and that frequency is selected based on how many excitations are there in the band. That's what leads to this kind of selectivity.
Is that what you meant when you said, I remember from the previous slide, there are some tricks you can play to get this to work out better?
Exactly. So for example, here we are using dispersive shift to select the frequency of these excitations.
Sure. Okay, cool. Mm-hmm. And then one last question maybe. Somebody asked if what the full scope is meant when people say characterization of these different types of systems.
Yeah, so the full scope is...
That's kind of a hard question to answer, but...
This is actually a hard question. I think the answer is even harder than the question because if you think about it, see, the problem of quantum mechanics is, first of all, this exponential phase space or Hilbert space, which we have to worry about, right?
Yeah.
So there's already exponential... it's not just the size of the space, it's also the exponential nature of the kind of states which exist in this space. So that is the problem. If you really want to characterize a quantum system fully, not only you have to be able to sample each physical system, you have to be able to sample all kinds of entangled states which can exist in these systems. And now you add noise to these systems, and then it's like, okay, now it is genuinely a computationally hard problem. So that's why what people, or at least quantum theorists and experimentalists, are trying to do is to try to certify certain classes of states which have proven to be computationally useful, like G and Z is used for quantum metrology, like W states or cluster states are used for measurement-based quantum computation. So we are not really trying to characterize the full Hilbert space at all. We are trying to reliably diagnose certain kinds of states. And as I said, even that is not easy because of the complexity of the space involved. So that is why the kind of method which I was talking about using eigenvectors, it's not going to tell you the information about all kinds of correlations. So for example, this one interesting point which happens in quantum systems is, let's say your Hamiltonian is two-body. So you have a two-body Hamiltonian, which is what I was showing, in this open chain. You only have two-body interactions, like for example, in this qubit-qubit interactions or qubit cavity interactions. Even a two-body interaction can generate an n-body correlation. And that is what we are able to detect. But this n-body correlation is different from the n-body correlation with which let's say a three-body Hamiltonian will generate. So depending on your generator, even though you are looking at k-body correlation, the nature of your correlation will change. So that's why this idea of co-design is so important, because you actually do need information about the generator of your interactions. You might be saying, okay, I have always a 10-qubit entangled state, but whether that 10-qubit entangled state was constructed using pairwise interactions or cubic interactions changes the kind of state you generate. So in some sense, the answer depends on the question. And we are just trying to confine the space where we have to look for these answers. You are basically saying, okay, I know that, I have been able to, using these eigenvectors, boil down my problem to the fact that out of 10 qubits, only 5 are entangled. And which 5 are entangled also I know. Now let me go there to those 5 qubits and do some kind of tomography to see do they have GHZ type entanglement or W state. So this is kind of like, kind of a background or to actually do your tomography on.
Mm-hmm.
Because even to find the subspace in which you should be running all those entanglement witness tests is not trivial.
Sure.
And that is the problem we are solving.
Yeah. I think that's a really good answer. Yeah, that makes sense. Really captures, just how hard it is these problems are. All right. Well, I think in the interest of time, we should wrap up here. But I really want to thank you again for joining us and for that really illustrative talk. And yeah, thanks so much.
Thank you. And thanks for your patience with my laptop not cooperating twice.
No problem. It happens to everybody sometimes.
Thank you.